Hey everyone, so this is the last video on the wave phenomena that I want to talk about, which is Doppler effect. This one's a little bit more, I guess, than some of the other ones like diffraction. But once again, it's something you just kind of need to recognize that it's occurring. So Doppler effect is a term that we're using for an apparent change in the frequency. Now, one thing that I've been saying a lot of the times is that the frequency doesn't change. If you send a light beam from air and it goes into water, into diamond, if it goes into outer space, it's not changing its frequency at all. However, there are some times where the frequency will seem to change. That while I may be sending out a type of red light, you might be able to witness it to be more like yellow light. And that's what Doppler effect is, the apparent change in frequency. Mainly, what this is caused by is you moving, you or the source moving. Basically, depending on how the two objects are moving relative to each other, it will make the frequency either go up or down. So if you're motionless, you're not moving at all, then there's no change in frequency. So this shows kind of a sound wave. So here we have a source that's not moving at all, and it's sending out a sound wave equally in all directions. You can see that the wavelength does not change as it goes outward. Uh, on the other hand, when you do start to move, you'll get a case that looks something like this. So if you notice, now that it's moving relatively fast compared to the wave it's sending out, you'll notice that over on this side, the direction it's moving towards, all the waves are going to start kind of getting closer and closer. That means that the wavelength is decreasing on this side. Over here, the waves start to lag behind each other, and the spacing between them ends up increasing. So the wavelength is going to increase on this side. Now, if this was sound, you'd end up hearing a much higher pitch here because now the frequency is getting higher, or at least it seems like it's going higher. For light, on the other hand, if something's moving towards you, you would end up seeing the light as being more blue in color. Over here, where the frequency is starting to kind of uh, get smaller, where the wavelength, the waves are getting further apart, the sound would actually sound lower in pitch, and light would end up looking a little bit redder. Because of the effect that it has on light, we would call this effect, where it's moving towards us, as resulting in a blue shift. And over here, this would be a red shift effect. So a good example of this, of like Doppler effect in real life, since we would never really see it happen with light because we're not going to be moving fast enough. But typically, this is like a train as it goes by, and it goes near, where you have that high pitch as it's coming towards you, and the moment it passes by you, the pitch drops and it starts sounding lower. If you end up moving at the same speed, which is typically called Mach speed, the speed of whatever in this case sound wave, um, then you basically won't hear it until it passes by you. Mainly because the sound's just kind of bunching up in the direction you're going. Uh, if you end up going faster than the speed of light, you get what's sorry, not speed of light, speed of the wave that you're moving. In this case, in the speed of sound, then you create what's called a sonic boom, basically caused by all the waves kind of bunching up together and resulting in a very powerful shock wave. A lot of times you'd end up seeing cones around the object. Let's see if I can find some. All right, so this is the thing that really bothers me is that I can't find sonic booms because I just get this. Awesome. Let's try this one. All right, so this does occur with light waves as well as sound. However, the only way we can do it, because as you know, particles cannot move faster than light in a vacuum. However, in water, light travels much slower. So, in nuclear reactors, we actually do get particles moving faster than light in the material. So, when you actually turn on reactors, nuclear reactors, you actually start to get this very ominous blue glow occurring. Um, I'm not even going to really pronounce this name, but I think it's called the Cherenkov radiation. That's the best that I'm going to get. But yeah, this is kind of Doppler effect for light. It's kind of cool. I'm clearly can't find a Doppler effect for sound because again, I can only find Sonic Boom, the video game pictures. All right. Now, Doppler effect is super important with astronomy because it mainly tells us stuff about stars. It tells us whether or not the stars are moving towards us or away from us, but it also tells us how fast they're going. Through the Doppler effect, we're able to find out things like that the closest galaxy to us, the Andromeda galaxy, is about to collide with us. That it's moving quickly. We actually know when it's going to collide with us. We know that every other galaxy outside of our cluster of galaxies are moving away from us and are actually accelerating away from us. So that's what the Doppler effect is telling us. It's kind of giving us an idea of where everything is in the universe, where it's going, what it looks like, and everything like that. Now, you should have learned in chemistry that every element has like a unique fingerprint called the spectral lines. Basically, the lines that they emit when a gas is excited and gives off light. Um, that's how we can identify certain elements of you know that make up a star or whatever. So using that known fingerprint, if we see the lines are actually shifted more towards the red side, then that tells us that it's moving away from us. And how much it's shifted tells us how quickly it's moving away from us. On the flip side, if we see it moving all shifted towards the blue side, then we know it's moving towards us. And again, the amount it moves is how fast it's going. Now, all you need to know are the terms that blue shifted is when it's coming closer together and that the frequency is observed to be increased. And when they're going further apart, the frequency decreases, and that's called redshift. Um, there's a bunch of phrases that some of them I've come up with. So you run away from fire, run towards water. Fire is red, away, red, towards blue, water is blue. Cars face towards you have blue headlights, and their brake lights are when they're faced away. The headlights are bluish. Brake lights are red, so away red towards blue. Um, this is another one. Rafiki has a blue face and a red butt. And then someone else wrote red to you or something. I don't know. I'm not even going to say that one. Blue to you. That's it. Blue to you. So here's a typical question that you would see with Doppler effect. So I'll pause the video, work on this yourself, and we'll go over in a second. All right. So here we have a car that approaches a pedestrian. The car blows its horn, and the sound wave by the pedestrian has a blank frequency. Well, since it's moving towards the pedestrian, it's going to have a higher frequency, a higher pitch because frequency and pitch are the same thing, and a lower wavelength. Frequency and wavelength have an inverse relationship because of v equals f lambda. So if frequency increases, wavelength has to decrease. All right, here's the next question. Pause the video, work on the stuff, and we'll go over in a second. All right, so here the car is moving once again moving towards the observer. We know that the frequency is going to increase, so that means that the frequency has to be some number higher than 350, so it's got to be 380. Now, one way you could have also figured this out is I told you how to identify if the frequency goes up or down, but I never told you how much it goes up or how much it goes down. So 320 and 330 are both lower than 350. So because we don't have an equation to calculate anything, you can immediately disregard A and B because, technically they would both, if the answer was a decreased frequency, they'd both be viable answers. All right. All right, here's the next question. Pause the video, work on this stuff. We'll go over in a second. All right. So they say that observer A hears a frequency of 512. Well, this source is producing a frequency of 512, so we know that observer A is not moving relative to this stationary source. So since this is not moving, A is not moving. However, B hears a lower frequency than 512. So that means B would have to be moving away from the source so that we get a lower frequency. So A is stationary, B is moving away. All right, and that's it. Well, if you have any questions, please let me know. Otherwise, I'll see you in the next one.